Hi, my name is Hardy, and I'm joined here by my friend Hans, and we are a group. We are in the same group for graduate project for Data 200 at UC Berkeley, especially for computer vision project. So the title is called Post-Disaster Classification Using Satellite Imagery, a feature-based approach to damage assessment. So for the next introduction about our data and our EDA, Hans will explain about that part.
So our title comes from the problem that is manual disaster damage. Labeling is slow and inconsistent, and our goal is to build fast, lightweight models using simple image features to classify both disaster type and damage severity. The process in general includes four main steps: data cleaning, EDA, modeling, and evaluation. In our exploratory data analysis, we use dataset as which consists to 26,000 images, and our EDA focus areas in image size distribution and damage level imbalance, color intensity patterns, texture and edge feature patterns such as Sobel, LBP, and Geber. And we found some key findings. First, there is a strong class imbalance with over 60% of the image labeled as no damage, which impacts model training strategies. Second, we observe that color intensity differs noticeably between testers. And we also note that Hurricane Matthew images tend to have smaller, more consistent sizes, while flooding and fire datasets shows greater variation, although size alone is not a reliable predictor. And for tax A, our goal was to classify whether an image shows flooding or wildfire damage. We use basic image features like the mean and standard deviation and deviation of the RGB values. We use mean brightness, local binary patterns or LBP, Geber filters, and our model is a logistic regression with five-fold cross-validation and scale features. Model appropriateness, simple, interpretable models suitable for clear feature separation.
Okay, so I'm going to explain about the task B, which is damage level classification. So the goal is to predict structural damage levels from the Hurricane Matthew dataset between level 0, 1, 2, and 3. So level 0 means that there is no damage in the buildings, and level 3 means that the building is destroyed. So the features, we use these features based on our EDA. The first one is mean and standard deviations of RGB. This is similar to task A. We use this because damaged buildings usually appear darker from the undamaged buildings and more varied. And we also use the mean brightness, also similar to task A, and also we noticed during our EDA that image size differs between damage levels, especially damage level 1 and 3. So we decided to include image size as our feature for task B. And also we use sabo edge, the mean values of sabo edge, because stronger edge indicate collapse of debris. So we decided that it might be useful to include sabo edge into our model. And finally, we also include local binary patterns, LBP, to capture fine texture irregularities. So the model itself, we are using random forest with certified five-fold cross-validations. And this is our improvement because previously we used decision trees and the results were below, the accuracy was below random forest model. And we also use hyperparameter tuning with grid search CV. So uh, this is the table of our parameters. We use n estimators of 50, 100, and 200, which is the number of trees in the forest. And also for the maximum depth of each tree, we use 3, 5, 10, and none. And last, for the minimum sample split, we use 2, 5, and 10. So grid search CV will find the best combinations between these values, and that will be our best results. And also we noticed that the dataset is very imbalanced between class damage. So we also include class weight balance into our random forest model to handle class imbalance between damage levels. And for the loss functions, we use impurity, which is the default loss function for decision trees and random forests. So why we use random forests? We decided that random forests generalize better than decision trees, and it also performs better than logistic regression. It can also model nonlinear relationships also, and handle class imbalance and also to reduce overfitting. So this is the result for our task A. We have tried several models and several features combinations before our final result. So our current result, we use logistic regressions with the features of colors, LBP, and also Gabor. It reaches about 98.4% of accuracy with F1 score of 98.56%. This is quite satisfactory, and we also uploaded to the Gradescope that our result reached the tier 3 threshold of 98%. So the main difference here is that LBP is the LBP features because like initially we didn't include that, but and we only reached about 91%. But once we add LBP feature into our model, both linear and logistics, we reach significant improvement for the accuracy for task A. And for task B, we initially use decision tree as our base model, and the features are color, size, and also sable age. And it only reads about 41.8% of accuracy, which only passed like tier 2 threshold. And we decided to improve our model using random forest and also add LBP to our mod into our model. And the model achieved 58.3% in terms of accuracy and 54.7% of F1 score. So as can be seen in the table here, that we also consider to add Gabor filter to our model, but by adding Gabor, the model reached lower accuracy, so we decided to exclude that feature in our random forest model. And also, we have already uploaded the result into the Gradescope, and we reached 56.7% for the threshold, so we reached tier 3. Hans, I think you're still mute.
Sorry. So this is like our last slide. We will um, add some discussion, possibility, and conclusion. So overall, from us, by adding texture feature like LBP, Sobel, and Geber, we were able to greatly improve classification results, and random forest model were more effective than logistic regression, especially for capture subtle difference between damage levels. And while our models can accelerate disaster response, there are ethical concerns such as potential misclassification and privacy issues. It's important to combine these models with human oversight. And so, in conclusion, lightweight models offer strong potential for supporting post-disaster assessment, and future work could focus on localized feature extraction and testing advanced ensemble methods. I think it's all from us. Thank you very much.
Thank you.